So as far as figuring this out, what you would need to do is first focus on, or at least where I would first focus, is focus in with your reagents and try and figure out what happens. What's your electrophile? So hopefully you'd have your cheat sheet set up where you would see those reagents and you would say, oh, the electrophile is Cl+. Okay. So then it's a question of where does that Cl+ substitute? Okay. So we're looking at substituting for hydrogens around that ring. Okay. Are all of those hydrogens the same? Does it matter which hydrogen you use?
I don't think so.
Okay. If we take a look at, oops, they're all colored the same. Let's make it a red hydrogen now. If we take a look at the red hydrogen and compare it to, well, no, they're going to be all colored. The green hydrogen. When the red hydrogen looks to its side, what does it see? When it looks to the right. When it looks to the left?
Hydrogen.
Take a look at the green hydrogen. When it looks to its right, what does it see?
It's the same on both sides.
It sees hydrogen versus hydrogen, which means are the green and the red the same?
No.
No, they are different.
Okay.
So that's one of the complications of once you put a substituent on the ring, that now makes all of the hydrogens different. You would expect different substitution patterns. Okay? And this is where we could go back and say the red hydrogen is the same as the one on the other side, and our green one is the same as the one on the other side. And that's where we get our ortho, meta, and para positions. Okay? So, which one of those should our chlorine substitute for? Well, if they're all different, we don't really know which one's better than the other.
Yeah.
Okay? Officially, what you should do, at least until you're super comfortable with this, is everybody's going to hate me, but what you should do is substitute at all of it. See what happens.
Okay.
So if we substitute for the red hydrogen, I'm going to draw. Get our CH3, we put our chlorine there. We aren't getting rid of the hydrogen, so we're doing this mechanistically first. So we're having the double bond come out and react with our chlorine.
Okay.
Okay. That puts a positive charge at that position. Okay, the other carbon.
Okay.
Because our electrons came out, we put the chlorine there, and we have to leave a positive charge. So that would be, what's that, our red hydrogens? Why is it this way? So we get, we'll call that the ortho. If we go through and do it at the other, one of the other positions, so I think I'm going to run out of space. Put the positive charge there. I'm missing something.
Double bond.
Yeah. What did I screw up? Oh, I grabbed the wrong positive charge. It helps if you actually look at draw the arrows from your double bonds. So there's where your positive charge is.
Okay.
Okay, and that would be the meta. Okay. What you should go through and do is prove that the ortho and the para generate the exact same resonance structures. The only thing different is where the chlorine actually substitutes. Okay. So because I don't have the space to do that, I'm not going to show that. So we'll just say para is our same as our ortho. Okay. So what we'll do now is draw out our resonance structures. CH3, double bond. CH3. Someone can feel free to whistle or sing, you know, so people at home listening now have something to listen to.
I want to hear my voice, that's for sure.
What are you saying about me then? Sorry, I gotta figure out where I was. Satisfied? See all the resonance structures there?
Yep.
Okay. So these are ultimately, and when we went through and did it in class, we looked at it in a different perspective. And that was only because we had atom X with lone pair electrons, we could draw resonance from atom X. With a carbon there, we don't really have those electrons, so it's a little bit more difficult to try and draw resonance, which is ultimately why that analysis, while it may look helpful, is technically wrong, where you're supposed to be looking as at the sigma structures. So you draw out these sigma structures, our intermediate resonance structures, and now evaluate those. Okay? So what makes all of those structures bad or high in energy?
The positive.
Positive charge.
They need
So let's
stability.
start with the meta. What can you tell me about the carbocation here? Can you classify it for me?
What do you mean classify?
So everybody asks that. How can I say it without trying to give away the answer? I can't. Primary, secondary, tertiary.
Tertiary.
How many carbons are attached to it?
No, secondary.
So it's a secondary carbocation. Let's move to the next meta.
Secondary.
And our last meta resonance.
Secondary.
Yeah, we can do that.
Okay. So we're going to go up and look at our paras now. What color did we say the para was? Blue?
Mm-hmm.
Come on. What kind of cation?
Secondary.
What kind of cation?
Secondary.
This is a pretty boring activity. They're all secondary. What's the last one?
Tertiary.
Interesting. We generate a tertiary cation when we go through and do our ortho-para substitution. Which is more stable, tertiary or secondary?
Tertiary?
Tertiary, which means which product is favored?
Tertiary.
Tertiary.
Ortho.
So what ends up happening is that our chlorine is now going to go to the either ortho or para positions because the methyl directs the chlorine to go there. Okay? So when we talked in class, we said, what's atom X? Atom X in this case, try and draw it over the top, of our carbon, or atom X attached to the ring, is carbon. Does that carbon atom have more electrons than a hydrogen?
Yes.
Yes, which means it is now an activator because it has more electrons to share with the ring, and it directs to the ortho-para positions. Okay? And one of the things that you may notice if you listen very carefully to when I talk about these is I always try and call it the para-ortho. Why do I call it para-ortho and not ortho-para?
Because the para is the most stable position between the two.
Para is favored over the ortho
Because it's further away.
because it's further away. When we go and look at how the reaction works, we have to take the pi electrons out, which means they're going by atom X with electrons. So if it comes out, it sees those electrons and potentially goes right back in. Whereas if we take a look at the para, if we bring the electrons out, hydrogen's not going to chase it away. So the para substitution makes a little bit more sense because it's less sterically hindered.
Okay.
So what I told you guys in class was that if you now predict the product of this, you should draw out your para substitution. Okay. Is the ortho still possible?
Yes.
Yes. So if you check answers in your textbook, almost all of them are going to show that you also have the ortho. Okay? Because para and ortho are possible reactions. We do not expect to see any meta because it's not a meta director.
Sorry, I'm.
Okay? As far as what your responsibility is for the class, what answer would I expect to see and give you full credit for?
Para.
Just for the para. If you draw the ortho, I don't know, depends on how many people do it, maybe you get extra credit because it technically can.
So this chlorine is positive, correct?
So
Coming off of that.
The chlorine,
Chlorine.
after it attaches, would become partially negative because it would take electrons away from the carbons. Okay. To get it to react with the ring is it has to be positive.
Okay. So that's why it's on the negative end, I see.
Yeah.
Okay.
Does that make sense?
Yep.
All sorts of colors.
That's a lot of work for one homework problem.